Hello. So let me first thank the organizers for giving me the opportunity to speak about our work. So our paper, Post-Quantum Security of the Sponge Construction, is available on ePrint. This is work done by me and Christian Schaffner from University of Amsterdam, Leon Groot-Broudering and Andreas Hulsing from Eindhoven University of Technology, and Domin Conro from Tartu. So let me start by reminding you what we mean by post-quantum security. So as we learned on the first talk of this conference, it's security that we care about when we already have a large-scale quantum computer, and the problem we're solving is defending against attacks of quantum adversaries that try to break classical crypto systems. And the usual motivation for all this is Shor's algorithm for factorization that breaks the RSA crypto system. Now, usually we only assume access to the quantum computer, but in this work we also allow for superposition access to the functions we are considering. So this is, well, the stronger threat model than only allowing quantum computations. So second part of the title says the sponge construction. So constructions allow us to take a function with a rather small domain and use it in a setting where the domain is increased, also codomain, but nice features of this smaller function are preserved. Now this reasoning is well, present because it's rather hard to construct good functions, so we often want to reuse them. So we focused on the sponge construction, and this picture shows how it works. So let me go into detail. So these two arrows here signify the state of the sponge. So function constructed with this construction using some particular f, and we modify the state by first XORing to the first r bits message blocks that we want to, so the input that we want to calculate on the sponge. Then we update the state by calculating the internal function on it. And then we continue, and the output is similar, but without this XORing, simply outputting the first r bits. And so the name sponge comes from the fact that we can divide this construction into two phases. One is absorbing, so soaking up water, and then you squeeze it, and output comes out. Now, this construction is used in many functions. The best known is a Kesak function that's behind a standardized hash function, SHA-3. And just to give you a feeling of those parameters, so the size of the domain and codomain of the internal function, these are, well, they sum up to 1600 bits. And okay, so now let me briefly remind you what hash function is. So we want to have a variable input length and a fixed output length function with the property that is collision resistance. Now, here I wrote quantum because all of that, in all this talk, I'll be caring about algorithms, efficient algorithms, so probabilistic polynomial time, but quantum, so they can both access this function h on superposition of inputs and do quantum computation. And now collision resistance is just the fact that probability of finding a pair of inputs such that they're different and they map to the same output is small, it's negligible, and this negligible function is in the security parameters, usually the output length, so n. Now, example of hash functions are the already mentioned NIST standard hash functions. So we have a family of, well, say 3 functions. There's also SHA-0, but it was broken immediately after, almost immediately after it was standardized. But SHA-1 is an interesting example of a function that was broken. So broken in terms of an explicit collision was found this year in CWI in Amsterdam. And this is a nice website where you can find out all about it. Now, the first 2 of the family are constructed with the Merkle-Damgard construction. So it's a different way of achieving this variable input length. And the last one, SHA-3, is constructed with the relatively new construction that we focus on. So before we go to this collapsingness, collision resistance is a feature of functions that is more or less classical. I mean, it was well, we were interested in cryptography since a very long time. Now, this property is not always enough when we consider quantum schemes, and because of that, the previous speaker introduced the notion of collapsingness, which is an upgrade to collision resistance that works, and it's much more quantum, so it works only in the quantum setting. And this is defined in terms of 2 games in which a pair of quantum adversaries exchange a quantum message. So this M is a quantum register, so it's a superposition of messages that all map to this value H. And A sends the superposition to B, and in one world in game 1, someone measures this quantum register in computational basis and sends the output to B. And in game 2, it does not happen. And if H, so if the hash function we're considering is collapsing, then the difference in probabilities that B outputs some particular bit is negligible. Now, right, so this means that I cannot prepare a superposition such that B could detect that it was measured or not. Now, to better understand what this all means, let me prove a rather simple theorem stating that collapsingness implies collision resistance. So this means that collapsingness is actually a stronger notion than collision resistance. Now we start with the contraposition of the above statement. So now from not collision resistance, we want to derive that H is not collapsing. So we start by using this fact. So A can efficiently find a pair of messages that will map to the same H. So it can prepare a equal superposition of those messages in the register M, the games on the previous slide. Now B will measure this register in some basis that contains this superposition. And this is the whole strategy of those adversaries. And now let's figure out what are the probabilities. So in game 1, there is a measurement. So only one of those states will be sent to B. Now, probability that B will measure this state in the superposition state is a half. And of course, if there is no measurement, then it's 1. So this, I hope this gives you an example or a good intuition, maybe some of it, to what this definition of collapsingness means, right? Because you see that, well, that if I subtract this from that, I get a half, which is not negligible. So, yeah. Okay, so for reasons that collapsing is stronger than collision resistance, and also that actually it's much stronger. So there is a separation example, which I'll not describe, but it can be shown that sometimes it is actually the feature you require. we focused on this notion. Okay, so this was the maybe introduction, also a reminder of stuff necessary to understand well what we proved. So we talked about constructions and hash functions, and hopefully, and I introduced the notion of collapsingness. And we prove that sponges, so the functions constructed with the sponge using the sponge construction are collapsing. We also prove that they are collision resistant. And if I will have enough time, I will tell you in briefly a modification to a quantum algorithm we derived, which might be easier to use. So what we did first, we proved that sponges are collapsing, namely that if we assume collapsingness of the internal function, and actually we consider just the first r bits of the output of the internal function as one function, and last c bits of the output of the internal function as a second entity, and we say that those are collapsing. And together with this zero preimage resistance, this implies, as we proved, that the big function, the sponge, is also collapsing. Now, zero preimage resistance means only that it's hard to find preimage of 0, of C 0 bits. Now, as you may remember, this is the initial value of the sponge construction. We always start with this value of the last C bits are always the first, in the first state that we encounter are always this. So, so the construction somehow requires that we couldn't prove otherwise that if you cannot, you should not be able to find how to go back to this initial state. But, okay. And the second thing is collision resistance. So here, as you see, I only changed collapsingness with collision resistance. So we may say that this is not very interesting because we proved the stronger notion, and why prove the weaker notion? Well, we also weakened the assumptions. So there might be a case that dividing this internal function into those two functions will give us only collision-resistant functions and not collapsing. And then we'll know that, well, it's still pretty okay in some applications. And the third thing we did in our paper, we modified, we made heavy use of unbiased collision finding algorithm, and modified the assumption that is required to use properly this algorithm, mainly that you have to be sure that there is a collision in the domain of function you're looking into, looking for collision in. And this is sometimes tricky and not so trivial to prove that there actually is a collision in the domain. So by using a random oracle, we managed to skip this. So we have an algorithm that works for any function, and so also, of course, for the sponge construction, for sponges using any internal function. So somehow, in some application, this might make your life easier. Okay, so this is the end. Let me remind you, we in the post-quantum setting, you don't only care for collision resistance of hash functions, but also about collapsingness, and also you can look at the easier to use algorithm. Thank you.